We're now covering volumes, and that's the disk or washer methods. So we are going to cover two methods to calculate the volume of three-dimensional objects. The first one is the disk or washer method, and the second one is cylindrical shells. Now again, it's advised that you draw a three-dimensional picture of the solid that you will calculate the volume for. I'll show you how to do that. So right now, in this lesson, I'm going to cover the disk or washer method. So again, we'll start off with some guidelines and then we'll apply them. So below are the guidelines to calculating the volume of a solid using the disk or washer method. Okay, if the solid, so there's basically two cases that you have to look out for. If the solid is rotated about the line y is equal to k, or they could say it has the line y is equal to k as its axis, then you're going to integrate with respect to x. So, for example, if the solid is rotated about the line y is equal to 2, or y is equal to 3, or y is equal to minus 5, whatever the case is, or if they say it is being rotated about the x-axis. Now, I just want to spend some time here. If it's being rotated about the x-axis, think about the equation of the x-axis on the Cartesian plane. The equation for the x-axis is y is equal to 0. It satisfies this condition. Y is equal to k. It's a y is equal to k line. In this case, k is 0. So if it's being rotated about the x-axis, you will go to this case. It's case 1. So you're going to integrate with respect to x. What do I mean by that? You're going to use dx. That's what I basically mean. And then the cross-sectional area will be in terms of x. Now I'll get to that in an example because it's best explained in an example. Okay, but what it means is since you're integrating with respect to x, obviously your integral needs to have variables that are x only. Okay, you can't have y's mixed up in there. So the cross-sectional area will be in terms of x. I like to represent that in terms of a of x. Okay, a stands for area, and then bracket x, the area is a function of x. It means it's in terms of x. I just like to represent it like that. Hence, your integral will be of this form here. So you'll just integrate your cross-sectional area, I'll show you how to find that, with respect to x from a to b. And obviously a and b are going to be x values because you are integrating with respect to x. All right. Then we have case 2. So if the solid is rotated about a line x is equal to k, or they could say it has the line x is equal to k as its axis, then you're going to integrate with respect to y. Hint, hint, dy. I just want to state one more thing here. If they say it's being rotated about the y-axis, think about the equation of the y-axis. That is x is equal to 0. So it's going to satisfy case 2. The cross-sectional area will be in terms of y, and it makes sense because you are, after all, integrating with respect to y. Your integral should have the variable y in it. It shouldn't have x in it. And I like to represent that, this here, the cross-sectional area in terms of y, as the area is dependent on y, or it's a function of y, or it's in terms of y. The integral that you will calculate is of this form. So the integral from c to d, where obviously c and d are both y values because you are integrating with respect to y, and you'll just stick your cross-sectional area in there. Okay, so that's the steps. It may seem a bit abstract right now, but I'm going to apply it directly in an example and you'll see how easy this section is. Okay, example 1. So pause the video if you want to try it on your own, but I'm going to walk you through this one and take you through all the steps. Okay, I'm going to start now. So calculate the volume of the solid obtained by rotating the region bounded by the curve. So let's start off with a 2D graph, then we'll go to a 3D graph. These are just 3D graphs, so I can show you what I mean with a bit more clarity. Don't worry about them right now. So Cartesian plane, here we go. Okay, bounded by the curves y is equal to x. So y is equal to x, there we go. X is equal to 0, so there's x is equal to 0, the y-axis. Okay, and x is equal to 5, there we go, about the x-axis. So we are going to rotate this region here that I am shading in white about the x-axis. So let's just sketch it a bit more clearly. Okay, so it's going to be this portion here, and it's going to go to x is equal to 5, right? And what I like to do is about my axis of rotation, or basically that's a fancy way for saying about the line that I'm rotating it. I just like to make this little arrow diagram to show me that, hey, I'm rotating it about this line, because the diagrams can get complicated. So there's the region here. I'm going to rotate it, right? So it's 2D, now I'm making it 3D. So we're rotating a triangular region about this. It's going to make a cone. Okay, so it's going to look like that. Okay, like that. Let's give it some depth. There we go. Okay, so it looks like a cone. In fact, let's take some drawings out. There we go. That's fine. So now it looks like a cone. So there's your x-axis, there's your y-axis. And now we can go to the drawings that I gave you. Okay, so let's use blue. This is what I have from the side view. It looks like a cone. Then I rotated it a little bit so this is what I actually drew. Just so you can see and get a picture in your head about what's happening. And this picture here, it's as if I'm standing directly on the x-axis and viewing it from the front. Okay, so it will look like a circle. So that's why the name disk and washer method comes in. Most of these look like disks from the front, and sometimes you will have washers, okay, where the center is empty space, but then you have a washer. Okay, so it's colored, or the area is basically like a donut. So that's what we have. That's just to give you an understanding of what we're trying to do. So the first thing to identify is, are we rotating it about a line x is equal to k or about a line y is equal to k? So we are rotating it about the x-axis. So we are rotating it about y is equal to 0. This is case 1. It means I must integrate with respect to x. So I'm going to be using dx. My cross-sectional area is going to be in terms of x. Okay, so great. I know I'm using dx, all right? I know I'm using dx. Let us get my cross-sectional area. So I just like to write it as a of x, area of x, and that's equal to. Now, this is probably the trickiest part of this. It's not really tricky. It's just the most confusing part of this. If you can get this, the section is a piece of cake. So what we are going to do is we are going to take a slice of this cone. We are going to take a slice of that cone and look at it from the side. And it is going to look like this. It's going to be in the shape of a circle. That's why it's called the disk or washer method. What is the area of a circle? Well, the area of a circle is pi. That's a constant number. We don't have to worry about that. R squared. The only thing we need to worry about is r, because that's a variable, that's a radius. What is the radius of this circle when I took the disk here? Okay, well, the radius is from here to here. Okay, so let me draw it on this diagram here. Let's take this circle here. What's the radius? Well, the radius is from the center of the circle to the top of the curve. Okay, so this is the radius. It's from the x-axis to the curve. Isn't that just a y value? Because it's from the x-axis to the curve, right? It would be, let's get this drawing out of the way. There we go. That's not what I meant to do. Okay, it's from this point here to that point there. It's a y distance. From the x-axis to the curve, it's a y value. So what's the y value of that point? Well, it depends on the x value that we are at. Okay, so we just take the x value that we are at and substitute it into the curve, and we'll get f of x. This is the y value. So what's f of x equal to? Well, f of x is equal to, in this example, the curve is f of x is equal to x, right? So this radius is actually going to be just a y value, but I know that the y value on any point of this curve here is equal to x because it's the linear line y is equal to x. If it was, for example, y is equal to x squared, right? then this distance would be y is equal to x squared, and my radius now would be x squared. Okay, but in this example, my radius is y, and y we know from the formula is equal to x because it's the linear line y is equal to x. So that is all I need to do. We have to have pi times r we found to be x, and then we are going to square it because that's how we get the radius, oh sorry, the area of a circle. Okay, so this is my cross-sectional area, pi x squared. And then the next thing to do, or last thing to do, is just set up the integral. So the volume, I'm going to write it with v, is equal to the integral. And since we are integrating with respect to x, we need to find the limits of integration. This is where the area starts, or the volume starts, and that's where the volume ends. It's from 0 to 5. Remember, 5 was given in the question. 0 was given in the question. So it's from 0 to 5, and we just insert our cross-sectional area in pi x squared, and then we use dx, and then you just have to solve this integral. When you solve this integral, the answer you are going to get is 125 over 3 pi units cubed. Okay, this simplifies to about 130.9 units cubed, if you're interested. Okay, so that's how you handle this example, right? Super easy, super simple. The only difficult thing is getting the cross-sectional area. Remember, it has to be in terms of x.